Hey Cam Champs, welcome back to Cam Champions with Chongtham David. In today's session, we're diving deep into Get Chemistry questions and not just solving them but mastering the concepts, shortcuts, and smart approaches behind each one, whether it's physical, organic, or inorganic chemistry. We shall tackle the most important and high yielding questions that have a strong chance of appearing in the actual exam. So get your notes ready. Let's crack it concept by concept, question by question. Now, let us first start with the technical section of question number 11 from 2024's exam. Among the following, the compound with the lowest carbon oxygen stretching frequency is given. These are manganese, vanadium, and chromium complexes. So, the carbon oxygen stretching frequency in metal carbonyl complexes is influenced by several factors, including the oxidation state of the metal, the electron density on the metal, and the overall electron withdrawing or electron donating effects of the ligands. So let's analyze the compounds. First, we have manganese. Okay. In option A, we have manganese compound. MnCO6. The coordination number is 6 and it exists in the cationic state. This is the coordination pair, and after ionization it has changed to cations. So the manganese in this complex is in a +1 oxidation state. The positive charge on the metal decreases the electron density on the metal, leading to weaker back donation to the carbon oxygen ligands, which typically results in a higher carbon oxygen stretching frequency. And let us now move on to the next compound formed by vanadium. Okay, vanadium in this complex is in a -1 oxidation state. The negative charge increases the electron density on the metal. It enhances the back donation to the carbon oxygen ligands, which typically results in a lower carbon oxygen stretching frequency. So it would look something like this: vanadium and carbonyl negative charge. To this, we can further expand the structure. Central atom is vanadium. Carbon. It has a tendency to form back bonding. Now, this is the carbon oxygen, and this carbon forms back bonding. And these are the 6 carbon oxygen ligands. In this, when metal is electron rich, then back bonding increases and the stretching frequency decreases. Case number 2. N3 chromium complex. Carbonyl 5. So chromium in this complex is neutral. And as you know, the oxidation state would be 0. The back donation to carbonyl is moderate, resulting in a carbon oxygen stretching frequency between those of the cationic and ionic complexes. Let us see the case of chromium, diene as the ligand, and also carbonyl is present. So chromium here is in a complex with a neutral ligand, that is diethylene triamine, diene, and 3 carbonyl ligands. The diene ligand is a strong electron donor, increasing the electron density on the chromium, which enhances the back donation to carbonyl ligands, and it lowers the carbon oxygen stretching frequency. So among these 4 given types of complex ions, vanadium would show the strongest, or the stretching frequency would be the lowest. So option B would be the answer for question number 11. Let us read the next question. The ground state of This chromium complex in +2 oxidation state is A5EG, 5T2G, 6A1G, and 6A2G. So let us explain the answer step by step. Complex and the electronic configuration. The complex here, let me write it here. Chromium, water, it has 6 water molecule as the ligand, and it is in +2 oxidation state, which means chromium is in the +2 oxidation state. And chromium has an atomic number of 24 with the electronic configuration of argon 3d54s1. In the +2 oxidation state, it loses 2 electrons. So it results in D4 configuration, 3d4. So this is the first step. And the next step is determination of the high spin complex nature. So chromium in this complex, hexa-aqua chromium 2, is a high spin complex because water is a weak field ligand and it does not cause large splitting in the crystal field. And as a result, the electrons prefer to remain unpaired in the higher energy orbitals rather than pair up in the lower energy orbitals. So it is a high spin complex. So this is the second strategy. Step by step, we're moving on from the electronic configuration to the high spin nature of this hexachromium 2 ion states. The next step is the octahedral splitting, delta naught, which is represented by delta naught. So in the octahedral field, the 3d orbitals split into 2 sets. The lower energy T2G set, which consists of 3 orbitals, dxy, dyz, and dxz. The higher energy sets comprises of EG set, which consists of 2 orbitals, that is dz square and dx square minus y square, because the lobes are along the internuclear axis and it passes through the internuclear axis. So they have the same energy. So D5 orbitals are separated into 2 sets, EG and T2G sets. So we are classified into 2. The lower one is the T2G sets and the higher energy is the EG set. It comprises of 2 orbitals here, and in the lower we have 3. So this is the third strategy. Moving on to the last step, the electron distribution. So since it is a high spin complex and the electron configuration is already known, 3d4, the electrons will fill the orbitals according to Hund's rule. 3 electrons will occupy the T2G sets, and considering, okay, we shall write it here in the orbital picture diagram. T2G has 3 electrons in the ground state. In such a manner, we have 3 electrons distributed out of this D4 configuration, and 1 electron will occupy the EG orbital. That is, this is already splitted. The d orbital is splitted into 2 sets, EG occupying the higher energy states, and out of this D4, 1 has already excited here. So this is the way how electrons are arranged according to Hund's rule. So thus there will be 4 unpaired electrons in total. So the ground state of chromium is, next step, we shall find the spin quantum number and the multiplicity. So the number of unpaired electron is 4. The spin quantum number S is the sum of the spins of the unpaired electrons. So since each unpaired electron has a spin of plus half, the total spin quantum numbers S would be 4 into 1 by 2, which is equals to 2. Now the spin multiplicity is given by the formula. So this is how we have calculated the spin, the value of S. And the next step is we can calculate the total spin quantum number of S as given by the formula, 4 into spin plus, okay, this would be equals to 2. Already we have calculated the value of S. The next step is finding the spin multiplicity. So what is the formula of finding the spin multiplicity? Which is related as 2s plus 1. So 2, the value of S is already calculated, which is 2. So the total number of the value of the spin multiplicity would be 5. The next step is ground state term symbol. This is the crucial part. So for a 3D4 configuration in a high spin octahedral field, the ground state term symbol, it is going to be determined by the electron distribution in the EG and the T2G orbitals. And many times questions are asked from this ground state term symbol. This is going to be a very important part. So let us find out the value of ground term symbols. The given complex is a high spin complex and it is splitted as given by the following. So we have already known that in the EG there are only one electrons here, and in the T2G we have three electrons, 1, 2 and 3. So we shall write here A1G, which is empty here. And in the T2G sets we have 3, T2G and T1G, and this would be A2G. So this above diagram shows the ground state term symbol for this complex is 5Eg, indicating that the total spin multiplicity is 5. I will write it here. The term symbol for this complex is 5Eg, right? So in this complex, the ground term symbol is 5Eg, indicating the total spin multiplicity is 5 here. And the ground state belongs to the EG level. EG level derived from the electronic configuration. So the answer would be 5Eg. Next, question number 13. The reaction of Genan fluoride with HNSO2F2 at 273 Kelvin in CF2Cl2 solvent yields. The reaction between this Genan difluoride and this salt, it is called difluoroamine sulfonyl fluoride. Difluoroamine sulfonyl fluoride. Shall write it here, the name. Difluoroamine sulfonyl fluoride. The reaction of Genan difluoride and this difluoroamine sulfonyl fluoride at room temperature, that is 270, not room temperature, at 0 degree, in the presence of CF2Cl2 solvent yields. So when this reaction occurs, I shall write it here down so that it is visible. So we now have this product F2, and the byproduct will be hydrogen fluoride. So this reaction involves the formation of Genan products, Genan compound, and the release of hydrogen fluoride as the byproduct. So the answer for this question number 13 would be D. Let us read the next question. Question number 14. The major product in the following sequence of reaction is. Now the reaction sequence provided in this above image involves a photochemical reaction followed by treatment with tribromo in solvent CH2Cl2. Here's a step-by-step explanation of the reaction. In the first step, we now have photochemical reaction, that is initiation of light at a wavelength given here is in terms of nanometer, 310 nanometer. Reaction condition is at 0 degrees Celsius. So the first step involves irradiation with light, that is H nu, at 310 nanometer, which is a typical condition for a photochemical reaction. It occurs at a low temperature, and and a low wavelength is required for this photochemical reaction to proceed. In this reaction, the carbonyl group undergoes a photochemical transformation, so leading to the formation of a diradical intermediate. This intermediate undergoes a hydrogen shift, 1,5 hydrogen shift, followed by cyclization to form a new six-membered ring, so which is a characteristics of 2,2 cycloaddition process. In the next subsequent step, it is treatment with BBr3 in dichloromethane. The second step, it involves this compound BBr3 in dichloromethane. BBr3 is a strong Lewis acid, commonly used to cleave this methoxy group, that is CH3O group attached to the aromatic rings, and it can convert them into the hydroxyl group. So in this case, the methoxy group on this aromatic ring is converted to a hydroxyl group, completing the transformation process. So the final product form after this transformation are shown in this step. So we are given here this starting material. The reaction conditions are 310 nanometer and 0 degrees Celsius. A strong Lewis acid in the presence of this dichloromethane is treated. Let us write the subsequent reactions so as to form the product. So in this first step, we will form a product here. And subsequently, this strong acid is added, BBr3, in the presence of dichloromethane. We now have the cyclization process will be proceed after this reaction. One, two, three, four. So here the methoxy group is present initially, so we now have the cyclization process in the next step. So eventually when there's no space, let me write here, the product would be, if cyclization is proceeded, the product would be A. So in this way you can easily answer this question. Let us read question number 15. Among the following, the chiral compound is, okay, P, Q, R, and S. Chirality in inorganic molecules typically occurs when a carbon atom is attached to four different groups, making it a chiral center. However, for alkenes, compounds with this carbon-carbon double bonds, chirality can also occur if there are different groups attached to each carbon of the double bond and the molecule lacks a plane of symmetry. So let's evaluate these compounds. The first compound, P. In this compound, P. First of all, let us see P. This is a nitrogen-containing compound having a six-membered ring with a different alkyl substituents. However, due to symmetry and the lack of a chiral center, it is not chiral, it is achiral. The next compound, B, Q. Here, this compound features a double bond with different groups attached to each carbon, that is either hydrogen, methyl and hydrogen. And this arrangement around this double bond creates two different possible stereoisomers, which may be either in the E configuration or Z configurations. So one of which can be chiral depending on the spatial arrangement of these substituents. Next, let us analyze this compound R. This is an alkyl triple bond, and since a triple bond is linear and the carbons involve only one substituent, this molecule is again achiral. Now for the fourth, that is the S compound. This compound has two methoxy groups and two other substituents, but these substituents are symmetric about the cyclobutene ring, making the molecule achiral. So from all this we can come to the conclusion that the chiral would be Q. That is, B is the answer for question number 15. Moving on to next question number 16. The major product in the given reaction sequence is Q. The mass spectrum of Q shows M is molecular iron peak. So phenol. When this is treated with sodium hydroxide and carbon dioxide followed by hydrolysis, let us first identify the probable product. So this would yield acid. It is a salicylic acid. Then further treat this with excess of bromine in the subsequent step by adding this bromine water in excess. We now have 2,4,6 tribromo phenol. So this is the required reaction we have. So the first step is, this is a name reaction. We call it the Kolb's or the Kolb-Schmitt reaction in general. So the phenol undergoes Kolb-Schmitt reaction where it reacts with sodium hydroxide and carbon dioxide to form salicylic acid, which is actually 2-hydroxybenzoic acid. And in the second step, bromination takes place. The salicylic acid is then treated with excess bromine in water. This leads to bromination at the third, fifth, and sixth positions relative to the hydroxyl group, yielding 2,4,6-tribromophenol. Now let us break down how the mass spectrum of this 2,4,6-tribromophenol would be calculated, because question is asking the mass spectrum of Q, which would be shown. Now let us understand the isotopic distribution of bromine here. Bromine, as we know, has two isotopes. What are the probable isotopes of bromine? The first is 79 and the second is 81. 79, it has a relative abundance of approximately 50.7%, and this 81 has a relative abundance of approximately 49.3%. So since there are three bromine atoms in 2,4,6-tribromophenol, there are various possible combinations of these isotopes. And now subsequently we have to determine the mass peaks. So we have to calculate the molecular ion peaks, that is M, M plus 2, M plus 4, M plus 6, based on the different combinations of bromine 79, bromine 81. So all the three bromine atoms are bromine 79. And in the subsequent steps, that is M, we have just clarified that this M, all the three bromine atoms are bromine 79 and M plus 2. This M plus 2, 2 bromine 79 and 1 is bromine 81. And M plus 4, in this case 1 bromine 79 and 2 bromine 81. 1 is bromine 79 and 2 is bromine 81. And M plus 6, all the three are bromine atoms. They are all bromine 81. So the relative intensities, this bromine 79, and bromine 79, all the three are bromine 79. We have just clarified here. So it would give rise to the abundance is 0.507 cube. This would be approximately equals to 0.1 130. The relative intensity would be 1. And in the same way, for this 2 bromine 79 and 1 bromine 81, we have to multiply with this relative abundance. So 3 into this, we have just calculated 507 is the relative abundance. It comes as square into 49.3. So the percentage of 49.3 would be divided by 100. It would be 0.493 square. So approximately it would come to about 0.378, and the intensity would be 3. So far we have 1 intensity and the third intensity, and so on. If we manipulate for this BMM plus 4, we have 1 bromine 79 and 2 bromine 81. So it would correspond to 3 intensity. And for this M plus 6, the intensity would be 1. So we now have the intensity as 1331. Therefore, the mass spectrum of 2,4,6-tribromophenol will show peaks at M plus 2, M plus 4, M plus 6 at 1331. Question number 17. The product M in the following reaction is. So as this given reaction, we have the Candida Antarctica lipase as enzyme, and carb is added to these reactions. For this reaction, we have benzyl alcohol. So the catalyst is Candida Antarctica lipase B. It is also known as carb. And the products, let us identify here: C6H5CH2OH. And this is acetone. Okay, so when we add this carb, there is Candida Antarctica lipase. The product will be benzyl acetate and acetone. C6H5CH2OCOCH3 and acetone. So this is a product we would be obtaining. So answer would be A. Let us move on to the next question. Question number 18. Critical micelle concentration CMC of a surfactant is 0.008 molar in water at room temperature. If the aggregation number of micelles is 80, the concentration of the micelles in molar concentration present in 0.088 molar aqueous solution of the surfactant at room temperature is. So as given, critical micelle concentration 0.008, and the total concentration is, surfactant concentration is 0.088. The aggregation number is, it's given here, 80. So we know the concentration of micelles can be calculated. So let us do the calculation here. Concentration of micelles is equals to concentration of surfactant forming the micelles. Let us divide this by the aggregation number. So where this concentration of surfactant forming micelles will be equal to the total surfactant concentration. So M1, let us say, subtract this from the CMC. critical missile concentration, let us call this as molar concentration, is 2. So according to the question, we have this M1, the initial concentration is 0.088. 0.088. The concentration of missiles present in 0.0 aqueous solution. Subtract this from the CMC value, that is, the concentration is 0.008. We now have 0.08 molar. So the concentration of missiles in the solution would be, it is also given, okay, from this value 0.80. So the concentration of missiles in the solution is 0.001. So how do we know this value? We can easily get the value by dividing this 0.80 respect to point by the aggregation value. Using this equation number 1, concentration of surfactant forming the missiles divided by aggregation number. So this is the value. Subtract this and divide by 80, the aggregation number, you will be getting 0.001 molar. B is the answer for question 18. Moving on to the next question, number 19. The order and the number of classes present in a group with the irreducible representation A1, B2, B1, B2, E1, and E2 are respectively. So to solve this problem, let's break down the information given. The irreducible representation as A1, we'll reproduce as A2, B1, B2, E1, and E2. Now the order of the group, this is the total number of elements in the group and the number of classes, the number of distinct conjugation classes in the group. So step 1 is to analyze this irreducible representation, and its irreducible representation corresponds to a distinct class of the group, and the number of irreducible representation gives the number of classes in the group, where this A1, A2, B1, B2 are typically one-dimensional representations. E1, E2 are typically two-dimensional representations. So there are 6 irreducible representations, which means there are 6 conjugatory, or you can say 6 conjugation classes. So let us determine the order of the group, which is the sum of the squares of the dimensions of the irreducible representation equals the order of the group, that is A1, A2, B1, B2, each contribute to 1 square. So can I say A1, A2, B1, B2 will each contribute to 1 square, that is 1, and E1, E2 each contributes to 2 square, that is 4. So the order of the group is 1 square, 1 square, 1 square each. We now have 1 square, 1 square, 1 square, and 1 square. Let's keep on adding. So we now have 1 plus 1 plus 1 plus 1 plus 4 plus 4, 4 plus 4, 8, 9, 10, 11, and 12. So the correct answer would be 12 and 6. Moving on to the next question, question number 20. The molecule XY2 is microwave active, and its vibration rotation spectrum shows only P and R transitions in the correct structure. So to determine the correct structure of the molecules XY2 based on its microwave activity and the presence of only P and R transition in its vibration rotation spectrum, let us break down the reasoning one by one. So the first step is microwave activity, and in this case a molecule is microactive if it has a permanent dipole moment. This requires that the molecule is not symmetrical in a way that we cancel out the dipole moment. And number 2, vibrational rotation spectrum, and this P branch involves transition with a decrease in the rotational quantum number. Rotation in the quantum number in the sense delta G is equals to -1. So the R branch involves transition with an increase in the rotational quantum number. Delta J would be plus 1. So the Q branch, which is absent here, would involve transition with no change in the rotational quantum number. So del J would be 0 here. So if this PQR line represents or present structure is band and PR line represents structure is linear for rotational, permanent and dipole moment. So this is the first part. Then the third subsequent step is regarding the structure. A linear molecule like carbon dioxide, which is symmetric in nature, has no permanent dipole moment. It would not be banned. It would not be microwave active unless the molecule is asymmetric, or has a bending mode that creates a dipole moment during the vibration processes. And the band structure like water molecule and it has certain permanent dipole moment and it is microwave active. So now let us give the total analysis of these statements we have given. The molecule XY3, this is microwave active. It must have a permanent dipole moment and it suggests the asymmetric structure. And the spectrum shows only P and R transition, which typically indicates that the molecule is not symmetric about its axis. And this is consistent with the linear structure where X is the central atom and Y atoms are not identical, creating a dipole moment. So given these points, the correct structure should be option C, that is Y is a central atom in the linear XY2. And this structure would represent or it would result in a non-zero dipole moment, making this molecule microwave active and show only P and R transition in its spectrum. So we can say this: Y is a central atom in linear XY2. Let us read the next question, number 21. The complex with distorted octahedral structures are: first we have vanadium, then iron, manganese, and followed by iron. So let us do the analysis of this steps one by one. In the first, let us consider iron with coordination number 6, 4 minus. The valence electron is d6. And the splitting of these d orbitals is, it is a low spin. The electronic configuration would now be written as T2G EG. So since there are 6 electrons here, we have to write here T2G 6 EZ 0. And the symmetric electronic filling would be taking place, and there would be no John Tyler distortion. So distortion would be, there would be no John Tyler distortion. So we can say conclusion is no distortion in the geometry. Let us analyze the manganese salt, manganese ion. The valence electronic configuration is D4. The splitting would be, it is a high spin. It's a high spin complex. The electronic configuration, since this is 3D4, we can write T2G, EG, 3, and 1. The symmetric electric configuration will be nil and distortion will be present. So John Tyler's distortion would be present. It takes place. Next, for the iron with coordination number 6, we have fluorine here, 3 minus. The valence electronic configuration is D5 and it is a high spin. And with regard to the electronic configuration, this would be, since it is D5, D2G3, EG2. The symmetric electronic configuration will be present, and so there is no John Tyler distortion. Next, we now have the last complex, that is the vanadium, VF6 3 minus. The valence electrons are D2. It's a high spin complex, and electronic configuration is T2G2 EG0. The symmetrical electronic configuration is absent, and Jahn-Teller distortion would be present, and it is a distorted octahedral. So we can conclude that the complex with distorted octahedrals are vanadium complex and manganese complex. So this is an MSQ type of question in GATE exam. There may be two or more options which can be correct. So A and C is the answer. We shall continue with the remaining questions in the next episode.